When should I use u-substitution? That's a good question, and I'll show you one way to think about it. So thanks to the fundamental theorem of calculus, we know that you can kind of go back and forth between derivatives and integrals. That's where we get the term derivative and antiderivative from. All right, so let's see. If you want to find the derivative of sine of x, you may know that to be cosine x. And now if we want to find the integral of cosine of x dx, we would say that that is sine of x. So as you can see, you can kind of go back and forth between the derivative and the antiderivative. Okay, so how does it help with u-substitution? So let's think of something else. Okay, so if I want to find the derivative of sine of 2x, I would need to use the chain rule. And I would say the derivative of sine of x is the derivative of the outside, cosine, keep the inside the same, multiply by the derivative of the inside. Okay, so that was using chain rule to find the derivative of sine of 2x. Right, now I have to use chain rule when my inside function is something other than x. Okay, so I chain on the derivative of that inside. Okay, now if I wanted to find the integral, or the antiderivative of cosine of 2x times 2 dx, then it should be just sine of 2x. So again, you can go back and forth between integrals and derivatives. So you can kind of go back and forth between chain rule and u-substitution. So how I like to think of it is if you would need to use the chain rule to compute the derivative, then you're going to need u-substitution to compute the antiderivative. Okay, and when you compute a derivative, you chain on the derivative of the inside. Now, when you use u-substitution and integrals, the derivative of the inside needs to already be chained on. So that's what we had here. The derivative of the inside was already chained on. So we can say we get sine of 2x plus c. All right, so let's look at another example. So if I want to find the integral of cosine of 5x dx, now, again, if I wanted to find the derivative of cosine of 5x, I'd have to use a chain rule. So now I know that if I want to find the antiderivative, I need to use u-substitution. Right, because I have an inside function, and this inside function is other than just x. It's a 5x. All right, now, like I said before, the derivative needs to already be chained on. And the derivative of the inside, that's not already chained on. We don't have a 5 chained on. But if it's a constant, you can always fix that. So we can kind of fix this with this clever trick. We could just multiply by 1. Right, that doesn't change our answer. That's still equivalent. And now we can leave a 1/5 outside and move a 5 inside. Okay, so now I have the derivative of the inside chained on. And now I can use u-substitution. So let's say u is equal to 5x, right? So the inside function is 5x. And now du is equal to, that's the derivative of 5x times dx. So that's 5 dx. Okay. And now I substitute. So here's my u, that's 5x. And here's my du, 5 dx. Okay, so now I substitute. In other words, I can replace things. So I have 1/5 integral 5 dx gets replaced with du, and cosine of 5x, that gets replaced with cosine of u. All right, and now I know what the antiderivative of cosine of u is sine of u. So then I have 1/5 sine of u plus c. And now you resubstitute, so your answer is back in terms of x, and you'll get 1/5. Let me write over here. So then you get 1/5 sine of 5x plus c. Right? Technically, it's this c would be different than that c, but okay. So there we go. I have 1/5 sine of 5x. So the antiderivative of cosine of 5x is 1/5 sine 5x plus c. All right, let's look at another example. Okay, so the antiderivative of e to the x, that is e to the x, right? And again, I wouldn't have to use u substitution here, and if I want to find the derivative of e to the x, I wouldn't have to use chain rule. But if I wanted to find the derivative of e to the 2x, I would have to use chain rule. So if I want to find the antiderivative of e to the 2x, I'm going to need to use u substitution. Okay, and again, I don't have the derivative already chained on, but as long as the derivative of the inside is just a constant, and then I can still find this integral. Okay. So we're going to let u be the inside function. So u is 2x. And now then du is 2 dx. Okay, now I have a dx, but I don't have 2 dx. And I can fix that by, I could think if I could divide in this equation down here. So I could say 1/2 du is equal to dx. So I just solved that bottom equation there for dx, because I do have a dx, that's right here. So I'm going to change dx to 1/2 du. Okay, so that makes the integral. I have the integral of e to the u. So now there's my u substitution. And now dx gets changed to 1/2 du. We usually like writing the constants out front. Okay, so now I have 1/2, and then the antiderivative of e to the u is just e to the u. And now I say plus c. Okay, now I resubstitute for x, 1/2 e to the 2x plus c. And there we go. So I use u substitution there to find the integral of e to the 2x. So again, I know you have to use u substitution to compute the antiderivative if you had to use chain rule to compute the derivative. All right, let's look at some other ones. We won't actually go through these, but we'll just talk about them. So let's look at something like the integral of 3x squared times ln of x cubed plus 4 dx. Okay, now I could compute this integral. So I could find the antiderivative. And I know I can because I have an inside function here. Let me get rid of these extra parentheses. Might be confusing. Okay, so I have my inside function. What's inside the ln is x cubed plus 4. And I need to know that I have the derivative of that inside already chained on. What can I do? I have the derivative of the inside chained on, 3x squared, right? So the derivative of x cubed plus 4 is going to be 3x squared. So I could find the antiderivative to this. And I would use u-substitution. Okay, how about, now what if I had something like this? The integral of x cubed, x to the 4th, plus 5 to the 50th power dx. Okay, now even though that's the 50th power, I can avoid expanding that out, multiplying x to the 4th plus 5 50 times and combining like terms and getting some power them. I don't need to do all that, right? Because I have an inside function, x to the 4th plus 5, and I have the derivative of that inside already chained on. Now I don't have exactly the derivative chained on, but it differs by a constant. So the derivative of x to the 4th plus 5, that would be 4x cubed. And that only differs between here, x cubed, just by a constant. One is multiplied by 4, one is not. So I can use u-substitution to figure this integral out. I wouldn't need to expand the polynomial out. Okay, so how I would do that, I'd say let u equal x to the 4th plus 5. And then that makes du equal to 4x cubed dx. Okay, now I don't have a 4x cubed dx, but I do have an x cubed dx. Okay, so I can solve this bottom equation for x cubed dx. That would be 1/4 du is equal to x cubed dx. All right, so then using u-substitution, have the integral of u, really don't even need this parenthesis here, u to the 50th, right? Because u is x, because x to the 4th plus 5 is u. U to the 50th, and now x cubed dx gets replaced with 1/4 du. All right, and now I could compute this antiderivative using the power rule for antiderivatives. Okay, something that might be good when you're first starting out with u-substitution, or whenever you need to, as a good check, is that you might be wondering, did I do a correct u-substitution? And you can check yourself by resubstituting in u and du. So by starting here, if I resubstitute u to be x to the 4th plus 5, and I change 1/4 du to be x cubed dx, just make sure that you get back to where you started up here. That can be a useful check. All right, so that's how you know when to use u-substitution for antiderivatives or integrals. Again, so if whatever function you're looking to find the antiderivative of, if you would have to use the chain rule to compute the derivative, then you're going to have to use u-substitution to compute the antiderivative. In other words, we can think if their inside function is something other than x. So again, here, my inside function, this isn't just ln of x, this is ln of x cubed plus 4. I need to use u-substitution. All right, and I know that it'll work with this one because I have the derivative of the inside chained on. And, you know, sometimes you don't have the exact derivative. So here's the inside. I have an inside function, x to the fourth plus 5. And I don't have the exact derivative chained on, but it only differs by a constant. So even though the derivative of the inside here is 4x cubed, I have x cubed chained on, so I can compensate by that. I can still compute that derivative, that antiderivative.